Well, I think we better start. I will make the announcements a little bit later, but first of all, I want to finish this chapter to introduce you to the idea of fiber bundles in mathematics. This is closely connected to the tools that we have developed, and what I will do is not really to prove or give any formal definitions, but to motivate the ideas, so that if you go and read mathematical books, you know how to relate to the physical problems we have discussed, and also why you want to adopt these kinds of concepts and terminologies, right? The idea of a fiber bundle, in some sense, just generalizes the idea of a function, which we use all the time, right? When we talk about electric field, a vector potential, normally, or wave function, we normally think about it as a function. We use these mathematical tools in physics almost without thinking. But the problems we have discussed over the last few weeks means that the ordinary idea of a function is not enough, and we have to go beyond the ordinary idea of a function, and that's what the idea of fiber bundles is about, right? Now, so what is the ordinary idea of a function? Let me take the idea of a wave function. A wave function, say psi of x, is a mapping between two sets. Always, when you have a mapping, you have what's called a domain and a range. The domain is a set that you map from, and the range is the set that you map into. All right? So when you have a function, the argument belongs to the domain, and the function value belongs to the range. So it takes x to psi, any x to any psi. For the sorts of problem we are dealing with here, the domain is just a manifold. It's just a set. It's not necessarily a vector space. It is a manifold with concepts of neighborhood, with concepts of infinitesimal displacements, but not necessarily with concepts of vectors or rectilinear coordinates. The range is a vector space, but actually the idea of fiber bundles can be generalized to cases where even the range is not a vector space. Could be another set, all right, and something else, some other mathematical structure. But we won't deal with that generalization. So we will only deal with mapping from, let's think of the base space as just space-time or space, all right, mapping into some vector space. Now, let me draw this picture differently. First of all, to align with the way you normally draw functions, and also to align with the way that mathematicians tend to draw these schematic diagrams when they discuss fiber bundles. If I sort of imagine that the function is a real number, although it really is not a real number, but you normally start from concepts of a real function of a real variable, right? So when you have a real function of a real variable, you would typically draw it like this, like when you write y equals f of x. The way you draw it is you draw x this way, y this way, and f is just a line here, right? That is how you would normally think of a function. So let's think of it schematically in the same way, even though in general, x is not one-dimensional, v is not one-dimensional. So you have the base space, sort of like x, the argument, and then the vector space, which is the function value, and the function is just a line in that on that plane, right? And of course, there are some conditions on this line. For example, a function, you can't have a function that goes like this, right? What you need is that for every value of x, there can be only one value of psi. Okay, there are some certain conditions on this line. So actually, the formal definition of a function is really this. A function is a subset in the product space, all right? The product space meaning this whole region. It is the set of all x and y. The set of ordered pairs, this is how we formally define the plane. In other words, the product space between B and V. So the curve is a subset of the space, which I call E, which mathematicians write as B cross V. And schematically, that means that whole plane. Okay? So a function is just a curve or a subset in this product space. So what is a product space? The product space mathematically means the following. It's the set of all ordered pairs, x and psi, where x is an element of B and psi is an element of V. That's always what you mean by a product space, right? So normally, it is the set of all x, y, where x belongs to this and y belongs to this. That's what you mean by a product. Okay? So that is what happens. Now, this is the usual idea of a function. The reason why we need to generalize this is the following. Think about the following function that, say, the vector potential, which is a function of, say, x, y, z, or x, y, z, t, doesn't matter. Okay? So it is a mapping that goes like this. All right? Like the example of the monopole that we discussed last time. So that is, normally you would think of the vector potential as a function of the spatial position. Let's forget about time for the moment. But in the monopole example, you see that we should not think of it as a single function, because a single function will not work, right? You cannot find a single function A that works for all of space. So this idea, you want to generalize it so that you do this only locally, but not globally, okay? For a small part of space, you can do something like what we have done in the previous few slides, but not globally. So schematically, the whole idea of fiber bundle is just the following. You want to make this idea precise. You want to define a space E, which is like the product space, but it's not exactly a product space. It is like the product space locally, but not globally. Okay? In fact, the simplest non-trivial idea is something you are familiar with, is the idea of a Mobius strip. See whether I can do it. So I have to make this thinner. You all know this. If you take a strip like this and you twist it around and do this, all right, so that it bends around like this. If I look at this set, which is E, think of this set as E. Then locally, if I take any small strip, that is like a product space, right? Product space means just a rectangle. Locally, it's like a rectangle. But globally, obviously, it is not like a rectangle, right? It is not like a two-dimensional Euclidean space, okay? So locally, you want to define something, a set E, which locally is like a product space with idea of a function, but globally it's not, all right? So let's see how that goes. Now, it turns out the way you do it is the following. How mathematicians formulate this is actually the following. It is actually a very clever idea. You start not with the base space and the range, not B and V, because that is not the fundamental concept. You start with the whole thing, like the twisted thing I discussed just now, all right? So that is a space E, okay? So you start with a space E, which is like the twisted thing, that's E. But somehow, you want to make it related to the base space and the vector space. Now, if locally it is related to the base space, that means for every point in here, all right, every point in here, it has to correspond to a point X in base space. Okay? So if I can locally think about it as a product space, the mathematical statement is that there is a projection that takes E to B. Okay? Just if you think about the ordinary case, that's just a projection. Okay? That's why we call it a projection. So there is a mapping from E to B, which we call a projection. So essentially, that gives you the first coordinate of the ordered pair. For every point here, you can associate it with a first coordinate. Is that all right? Now, if you have a projection, then you also have the inverse map, which I call pi inverse of x. That means all members that project to the same x. Okay, so I have the inverse map, which takes every x to all points which project to the same x. That really just organizes this whole space, which originally has no structure. It's just a set of points, right? Organizes it, if you like, into lines like this. So that effectively tells you you can draw lines like this here. All points on the same line project onto the same x. Okay? And mathematically, that is called pi inverse of x. It is the inverse map that takes x to all points that maps to x. So schematically, you have E, then you draw these vertical lines and associate each line with an x. Okay? So really, this red line is already does it for you, because this red line must somehow be the same as the vector space V. Okay? Think about it. If I do this, okay? So what I have done, imagine this is twisted. So on the twist, I draw a line. Okay? This line locally is the same as the y-coordinate, right, of a rectangle, of ordinary plane. Okay? So what I now next want to make precise is the statement that this red line, each of these red lines, is similar to a vector space. Okay? If I'm talking about the vector potential, this is three-dimensional space. This is the vector space that describes A. Okay? Oh, but I think I need to go beyond this. Oh, so what we have is the following. So we say that for each of these red lines, which I call pi inverse of x, is the same as the vector space V. Mathematicians state this by saying that there is a vector space V and a mapping from V to this red line, which is some sort of isomorphism, okay, which preserves various things, continuous. If it's a vector space, it preserves inner products, whatever. Okay, so there is a mapping that essentially preserves things. Okay, but actually, these mappings can be extended, not just one mapping for each point, but one mapping for a set. That is, you can actually have the same mapping for a certain range of x. So this is an open set, which I call B alpha, and the same mapping applies to the whole set. And this mapping I then call phi alpha for the open set alpha. In the example of the monopole, actually I only need the two sets. One is the northern cap, one is the southern cap. And for the whole northern cap, I have a single mapping, right? So a single vector space, a single function will do it. All right? And the question now is, the whole space, of course, is covered by a number of open sets. In the monopole example, we needed only two. But in general, there could be any number. There would be points x which lie in the overlap between two sets. So in this set, if I regard this point as belonging to open set B alpha, there would be a mapping, phi alpha, that takes you from this, the vector space to the red line. If I regard it as a point in B beta, then there will be a mapping from V also to the red line. But if I now go like this, phi alpha and then phi beta inverse, okay, if I do this, take V, go to the red line and come back, and call this composite function G, that is a mapping of V onto itself, okay? And that is a transformation on V. Take the monopole example. That means I take one vector function potential and another vector potential. The vector potentials are all defined on V. And this is the transformation that takes one vector potential to the other vector potential. Okay? So that is a transformation from V back to V, and it must form a group. This is the group of all gauge transformations. Okay? So this mapping generates a group of all of transformations on this space. In our example, this would be the gauge transformation. Okay? So if V is a vector space and G is the linear group on V, otherwise it could be any group. And so this is the idea of a fiber bundle. This is how mathematicians define a fiber bundle. You have a set E for which there is a projection. The inverse projection, the red line, is homeomorphic to some vector space. All right? the same vector space, but the homeomorphism could be different for different open sets. And in overlapping regions, you then define through this process a group transformation on the vector space V. Okay? So that structure is called a fiber bundle, right? And this is called a fiber. The whole thing is called a fiber bundle. This is called a fiber, okay? And this is, so if you open a book in mathematics, they will start giving this sort of definition, okay? And without motivation, you don't know why they would want to define something like this. You see this without having gone through a physical example. You probably don't understand why they want to discuss something like this. So the key idea is that there is a private vector space, private in the following sense, that this mapping cannot be extended to the whole space. You need, say, one mapping for this part, another mapping from another part. That is the mathematical precise way of saying that the vector space is private. It is the transformation between the mapping between the red line and this vector space can only be defined over local patches and not globally. Okay? And in the overlap region, they differ by transformation. Okay? So that is just to introduce you to the language of fiber bundles. Okay, now I want to, I promise you to sort of lead you through the last problem set, so that you don't have to do it yourself, which is a very simple way of deriving the monopole quantization condition. Okay, this is problem 32. So the problem I will discuss is the following. Is the head-on collision between a monopole and a charge. That is, in fact, the title of the article we wrote, Head-on Collision Between Charge and Monopole. Okay? So what happens? In fact, the reason we got into this problem was the following. When Professor Yang taught this course, I don't know, nearly 20 years ago, not exactly this course, but something similar, he discussed what happened when you have an electron scattering off a monopole. Okay? And of course, at non-zero impact parameter. So you have the monopole here, the electron coming in, what happens? Okay? Classical problem, right? So you have a point particle, so you have a radial magnetic field, so you just apply the Lorentz force law and look at what the trajectories are. And he said that the head-on collision is very tricky. Think about it. What happens in a head-on collision? What do you think happens in a head-on collision? Well, the electron, the charge, comes in. The velocity is radially inwards, exactly radially inwards, right? The magnetic field is exactly radially outwards. So the velocity is always parallel or anti-parallel to the magnetic field. V cross B is 0. So the force is 0. So nothing happens. Okay? Now, nothing happens when it gets to the origin. What happens? Does it bounce back? Does it go straight through? It's a little bit tricky. You have a singular situation, right? Which is a little bit tricky. So how do you handle it? And I want to go through this slightly because it also illustrates how we approach problems in physics. It is singular. Why is it singular? It is sort of like 0 over 0, right? Why? Because the magnetic field is 1 over r squared. At the origin, you have a 0 in the denominator. But V cross B has a sine theta for the cross product. That is also 0, right? So it's sort of like a 0 over 0 situation. And we can't be naive about it. Well, the way we would do it is to regulate. because the 0 over 0 comes about because we imagine these to be point particles. Let's assume it's not a point, then you won't have 0 over 0, right? So let's assume the following. The monopole is a uniform sphere of magnetic charge. And eventually, I will take the radius to 0. That's how you do it. Now, you won't have 0 over 0. First of all, the magnetic field never goes to infinity, right? Because you have the magnetic charge distributed over a sphere. That's just like the case of charges. Secondly, the sine theta is not always 0. Because the magnetic field, let's see, the magnetic field, okay, let's keep going. To do this, let me just take an even simpler problem. An electron hitting a ring of charge. Okay? Where this is the z-axis, this is the xy plane. Okay? So what you have is a ring of, not charge, ring of magnetic charge. And the, sorry, I want to do it the other way. Yeah, the other way is better. Same thing, actually, all right? So this is a monopole hitting a charge. Okay, so this is a sphere of charge, this is charge. Yeah, okay? So I take a ring of charge in the xy plane, and I shoot a monopole right down the middle. And this is a z-axis. And I ask what happens. Is that okay? And later, I will superpose many of these rings to form the sphere. Because a sphere can always, first of all, be sliced into disks, and each disk can be thought of as little rings in the xy plane. XY plane is perpendicular to the motion of the magnetic monopole. So as the monopole goes through, the monopole goes this way, what will happen, all right, to the sphere? And you can imagine the monopole go through slowly, rapidly. It will turn out not to matter. Now, there will be a flux. All the magnetic field lines will be going through like this, right? So there will be a flux through the ring, which is increasing. So if I plot the flux through the ring as a function of time, initially it will be 0, so very far away, almost no flux goes through the ring, right? When it gets to here, half the flux will go through the ring. Because the total flux that comes out this way, half would be going this way, half going that way, right? And what would half be? Half would be 2 pi g. So when it crosses here, whatever time, it will go. Okay? I don't know how the curve looks like halfway in between. It goes from 0 to 2 pi g. Because the total flux is 4 pi g, right? The magnetic field goes like g over r squared. You integrate over surface, that is 4 pi r squared. And when it gets exactly to the plane of the flux, half the flux would have gone through. Right? All the flux on this side. So as it comes through, the flux would be changing. If the flux is changing, Faraday tells us there will be an EMF along the direction of the ring, okay? So let's see what happens. If there is an EMF along the ring, and the ring is charged, then the ring will start to rotate, right? Will start to gain angular momentum. Is that okay? So let's see what happens. Let me call the total charge on the ring, let me call that Q. So how will this rotate? What would be the rate of change of angular momentum of the ring? All right, along the z direction. It will be the force, the tangential force, times the radius of the ring, right? So you have the ring. There will be a tangential force, which is actually distributed evenly around the ring, and multiplied by the moment arm. The tangential force, total tangential force, would be the total charge times the electric field. The electric field is a tangential electric field. And the tangential electric field would be the EMF divided by 2 pi r, right? Because you have an electric field that is going around. The line integral of the electric field is the EMF. Is that okay? Let me draw another picture. Here is the ring. And the E field goes, say, like this. Always tangential, okay? So the EMF is E dot dr. Never mind minus signs, is E times 2 pi r. By Faraday's law, so I cancel an r, the EMF is the rate of change of the flux. Never mind minus signs, okay? That's just Faraday's law. Okay? Now, but this equation, very happily, I can just integrate. Because both sides are time derivatives, I don't have to understand what this curve looks like in the middle. I integrate. Then from beginning to end, I have delta Lz is Q over 2 pi delta phi. So half delta phi is how much? Is 2 pi g. Right? I just draw there. So this is equal to Q times g. That is the change of angular momentum of the ring when the monopole has come right to the middle. Now you can do the calculation for the other half from the middle all the way to infinity on the other side. This is from, say, minus infinity to 0, all right? So from minus infinity to infinity is 2q times g. So just proportional to the charge on the ring. Now I add up all the rings, okay? So delta Lz for the whole sphere is just adding the delta Lz for the individual rings. So you just sum these things over the individual rings. So you sum the q's over the individual rings. And the sum of all the q's is just the total charge of the sphere. Okay? And this calculation is valid for a sphere of charge. And I have used a non-zero radius in the intermediate steps. But the final answer is independent of the radius. So I take the limit radius going to 0, still valid. So that is what happens when a monopole goes right through a charge. The charge starts to spin. It gains an angular momentum. Right? The physical picture is very simple, even before you do the calculation. As the monopole approaches, the flux changes. So Faraday tells you there's an EMF that goes this way, and that causes the charge to spin. Okay? So after the monopole has gone straight through, the charge, if it originally was not spinning, now begins to spin. And the minus, you are careful about the minus signs. That tells you whether it's spinning this way or this way. So the change in angular momentum of Z component of the charge in the whole scattering process from time minus infinity to time plus infinity is 2 times E times G. But the angular momentum in any direction must be quantized in steps of h bar. Even if it's half integral spin, it goes from minus a half to plus a half h bar. Okay? So the change must be an integral unit of h bar. Okay? It can be 2 units from 0 to 2, that's allowed. From 0 to 2.1 is not allowed, right? Units of h bar. So that tells you that this condition for the quantization of monopoles. And it's exactly the same as the one we did using 2 vector potentials. Now, the tail end of this problem, there are 2 small parts that I leave to you to discuss and as part of the assignment. This you don't need to do, right? And this deals with the following paradox. Oh, this this starts with 0, actually probably to time minus infinity somehow, right? Okay, so it's very far away. It goes to 2 pi g. What can you say about the flux when it goes over to that side? What is the flux at t equals plus infinity? Must be 0, right? Must go back to 0 eventually. When the monopole is very far that way, the flux through the ring must be 0. So how does the curve go after this plane? Well, think about it. Suppose this is the plane. Just before the monopole reaches that plane, nearly half the flux going this way is going through the ring, right? So call that plus 2 pi g. Immediately after it has gone through the ring, nearly half the flux this way is going through the ring. All right? So that should be minus 2 pi g. So somehow this curve should go like this. Right? Now, something is very strange. Because if this is really the case, then I integrate this equation from minus infinity to plus infinity, then would be the flux from minus infinity to plus infinity, I would get 0. Right? The change of flux between this point and this point is 0. I cheated just now. I did 1/2 and then multiply by 2. The change of flux from here, compare these 2 points, is 2 pi g. But compare these 2 points, it's not twice the amount, but 0. That's mystery number 1. Mystery number 2 is that there is a sudden change of phi. Phi goes through a step function, so d phi dt goes through a delta function. So the force has a delta function. So suddenly there is a very big force. But you know that can't be the case, right? As the monopole goes through that plane, nothing is singular. There should be no infinite EMFs or infinite forces. All right? So these are, of course, all related paradoxes. Okay? I avoided it by doing 1/2 and then multiplying by 2, which avoids this problem of crossing the plane. But you know nothing unphysical or infinite happens at the moment when you cross the plane. So there is a little bit something that I haven't completely told you about. Okay? And I leave that as an exercise for you to think about. Hint. The hint is similar to something you have learned in the displacement current when you first learned displacement currents. Okay? That's the hint. So it's not anything very fancy. So you see, this is except for that little tricky part. This derivation is very simple. No vector potential, no difficult integrals, no nothing. All you need to know is what? Faraday's law, the force on a charge, concept of moment, and the fact that angular momentum is quantized in units of h bar. Okay, that's where we slip in quantum mechanics. Okay, so that's it. Now, I think I should now make some announcements. First of all, you know the time of the exam. I'm going to put down the screen just now, so let me write this down. Is Thursday, 14th of December, 9:30 to 12:30, University Gymnasium. All right. Secondly, for the homework, I have assigned up to a certain number of problems to be handed in this Wednesday. There are a few remaining problems. All the remaining problems next Wednesday. Although there's no class, you can hand it in to UNO. Okay, I think there are about 4 or 5 more. And for this particular problem, you don't have to write this out. Just deal with the last bit. Okay? And I think the way we are going, we won't need to, we have a make-up session scheduled for Friday, just in case we can't finish in time. But I think we can. We still have an hour today, nearly an hour today, and then we have 2 hours on Wednesday. And I hope I will be able to cover the final chapter. And we don't need to meet on Friday. Okay. All right, so in this final chapter, I want to take the tools we have developed, go one little extra step, and you should essentially arrive at much of the mathematical formulation of general relativity and the concepts in Riemann geometry. Okay. Of course, I can't derive the laws. That's a separate law of physics. But at least when you adopt the natural language, the laws will appear very natural. Okay. Of course, you know that general relativity is the theory of gravity that supersedes Newton, and it describes space-time as curved. And therefore, in order to write down the mathematics of general relativity, you first of all have to understand the mathematics of curved manifolds. Now, what is meant by a manifold? A manifold is a set that is locally similar to flat space, or flat space-time. If I talk about space, you take flat space, and you just think of a local distortion, make it curved. Okay, so or space-time. Now, space would be Euclidean space. Space-time, before you distort it, would be Minkowski space. Minkowski space simply means that the distance is minus dt squared plus dx squared plus dy squared plus dz squared. All right, so that is a minus. Of course, I will use units where c is equal to 1. So the first thing is a manifold. A manifold does not necessarily have a concept of distance. A Riemann manifold is a manifold that has the local concept of distance. Okay. So a Riemann manifold essentially has a generalization of this expression. Okay. So if I move by an infinitesimal distance dx, then there is a quadratic function that tells me the distance between the neighboring points. So what I will quickly talk about, and for those of you, I think many of you here already took the course in general relativity, so this will be largely familiar, but I just want to connect with things that we have talked about in this course and show that at least the mathematical language is actually a special case. Right? And in fact, many of the slides is really adapted from that other course. So I will quickly go through the concepts of manifold and coordinates, the distance and metric, the concept of vectors, and then how the concept we have developed here, connection and curvature, appear in general relativity. And then, using that tool, I can then state the laws of general relativity in a very simple way. So start with manifolds and coordinates. So start with the terminology. A manifold is just a set that is locally like either Euclidean space in n dimensions or in Minkowski space in n1, n2 dimensions. Now, Minkowski space in n1, n2 dimensions is just a generalization of this, where, say, there will be n1 coordinates that appear with a positive sign and n2 coordinates that appear with a minus sign in this generalization of the Pythagoras theorem. Okay? So the normal Minkowski space that we talk about is 3, 1, 3 positive components and 1 negative component. And loosely speaking, we will often, instead of talking about manifold, use the word space. And this is not to be confused with space in space-time. It's just another mathematical terminology. All right? Now, on a manifold, think of a curved surface as a manifold. The first thing you define are coordinates. Now, when you first learn about coordinates, it's in terms of Cartesian coordinates. Cartesian coordinates actually at the same time serve a number of different functions. It serves the function of distance as well, right? So in Cartesian coordinate, let's say you go from x equal to 1 to x equal to 3. The distance you travel is 2. Okay? So coordinate defines position. I give you coordinates that tells you where the point is. Secondly, note when in Cartesian coordinate, that tells you the concept of distance. Number 3, it also carries the concept of vectors. Because if I go from, say, the origin to the point with coordinates, say, 3, 4, you think of it as identical to the vector pointing from the origin to 3, 4. It is a vector with x component 3, y component 4. Right? So normally, when you first learn coordinates, Cartesian coordinates, 3 concepts are bundled together. One is a specification of position of a point. Right? I give you coordinates that tells you what the point is. Secondly is a specification of distance between points. Change of coordinates is equal to distance, at least if you move along one direction. Third, it is associated with vectors. 3 concepts bundled into one concept. Now, on a curved manifold, we have to separate these 3 concepts, disentangle 3 concepts. Coordinate serves only one function, is to specify a point. Does not tell you anything about distances, does not relate to vectors, at least not in a simple way. Okay? So coordinates serve only one function. And I will write coordinates as x superscript mu. So mu, say in 2 dimensions, mu would be 1, 2. And if they serve only to specify positions, you can think of it as drawing grids. So I draw 2 sets of lines, say on 2 dimensions. So this green set, this line is x1 equal to 1, 2, 3, 4. The blue set is say x2 equals 6, 7, 8, 9. I denote these with upper indices. That's just a convention. The 2 sets of coordinates need not have the same units. For example, if I use polar coordinates, then what I'm doing is one set of lines go like this, and they tell me phi equals 0, 45 degrees, 90 degrees. And the other set of coordinates, they should all go through the same point, all right? It's r equal to 1, r equal to 2, r equal to 3, okay? So that's one could be an angle, one could be a radius. And if I draw 2 sets of grid lines, then if I give the 2 values, I will specify the point. So if I'm talking about that point, then that point is described by the coordinates. The first coordinate is 3. That means it lies on this line. The second coordinate is 9. That means it lies on that line. Okay? So the coordinates simply specify a point. They are denoted by upper indices. No such thing as x with lower indices. And it is not a vector. Okay? Among other things, if the surface is curved, say surface of a sphere, to go from one point to another point is not even a straight arrow, right? Because a vector is a straight arrow. That is the concept we want to formalize. Right? So this is just specifies the position. Now, many coordinate systems are possible, and physics must be independent of the changes of these coordinates. Now, this is very similar to what we have discussed just now, the idea of fiber bundles. Because if this is the base space, then you must divide into coordinate patches. And on each, you can have a different set of coordinates, and the coordinate patches together cover the whole space. Think about the following. If I take the surface of a sphere, I can use polar coordinates. But actually, polar coordinates does not work at the two poles. They are singular. The polar coordinate is singular at the two poles. Okay? So what I could do is I exclude a small northern cap, I exclude a small southern cap. Polar coordinate works sort of around, say, from minus 80 degrees to plus 80 degrees, let's say. So that is one patch. But I can have another patch where I have polar coordinates defined with respect to this axis, right? So it goes around like this, and I exclude these two caps. The two together would then cover the whole space, okay, if you do it right. You cannot have a single, you may not be able to define a single set of coordinates that covers all space. And whatever physics we want to discuss must be independent of changes of coordinates, because coordinate systems are arbitrary. Now, the second concept is the concept of distance. And the central question is, what is the distance, which I call delta S, related to a change in coordinates? Really, the generalization of this law. Okay? So if I have one point with coordinate x1, x2, and another point where x1 changes by a little bit, x2 changes by a little bit. Now, all the deltas would, in the end, be infinitesimal. What is the distance between these 2 points? That is the question I want to specify. And Riemann geometry says that distance, if I'm talking about these 2 points, P and Q, right, with positions x1 to xn, and the other one, each one is slightly increased by an infinitesimal amount, that the distance is a quadratic expression in the infinitesimal displacements, okay? Where the coefficients, of course, can depend on the position. That is the assumption under Riemann geometry. Now, you can take that as a postulate. That would be axiomatic Riemann geometry. Or you can sort of prove this in the following way. If I start with ordinary flat Euclidean space and just take a surface in it, okay, set a constraint, then you can prove that this is always true, that it will always give you a quadratic expression. Okay? Now, the reverse theorem is also true, but it's much more difficult to prove. Now, let me repeat what the two theorems are. The first theorem is that if I take Euclidean space, the same is true of Minkowski space, but let me be simple, Euclidean space, in some high dimension, let's say 20-dimension Euclidean space, and I take a subset by setting a certain constraint. The simplest example is this. I take 3-dimensional space, and I set the constraint x squared plus y squared plus z squared equal to 1. Okay? So that describes a surface, which is the surface of a ball. Right? So in general, you have a lot of coordinates, Cartesian coordinates. Distance is given by Pythagoras theorem, the simple Pythagoras theorem. But I set certain constraints. The points that satisfy those constraints would lie on a lower dimensional surface. Okay? If I set 10 constraints, the dimension would be lower by 10. Okay? Then you can easily prove that on that surface, the distance is given by a quadratic expression like this. Okay? So that is something you can prove very easily, subject to usual assumptions about how smooth those constraints function are, they are differentiable, and so on. The reverse theorem is the following. If I give you an abstract space and tell you this is true, that the distance is given by a quadratic expression, then you can always regard it as a subset in a larger dimensional Euclidean space. That is, it can be embedded in a larger dimensional Euclidean space. Now, how much larger could be more than one dimension more? could be 20 dimensions more. The mathematicians only proved the theorem that it can be done in finite number of dimensions. Okay? And that is why, for those of you who have taken the relativity course, I did all the calculations starting from the larger space, which is Euclidean. The reason I could do that was because of this reverse theorem proved by mathematicians, that even if it is purely abstract, I can always do that embedding. And the reason why that is convenient is that if I start in a larger space, I know exactly what is happening, because that is just normal analytic geometry generalized to more coordinates, right? Okay. So just to unify notations, A I would call G11, B I would call G12, this I would call G21, and so on, just so that we have a systematic notation. And of course, even more compact notation is I write it as G mu nu, dx mu, dx nu. The summation convention, of course, applies to repeated indices. Right? So this is the generalization of the Pythagoras theorem to the following, that the distance must still be quadratic, it need not be diagonal, and the coefficients need not be constant. The coefficients could depend on position. And so G with two lower indices is an n by n matrix, and I will define G with the upper indices as the inverse matrix. So I just invert this matrix. And given anything with upper coordinates, I will define the object with lower coordinates by using G to lower and also the inverse matrix to raise. Now I come to the concept of vectors. And how did you learn vectors in high school? Well, you start with a displacement, and other objects with the same property are also vectors. And we adopt the same strategy here. Now, the usual definition, the displacement is the prototype vector from a point A to another point B. And that is like a straight arrow. So that is what I have in mind when I say a vector. Now, on a curved surface, this is not a vector, right? So suppose you think of the surface of a sphere. And again, I try to start with displacement from a point A to a point B. That is not a straight arrow. And if I call that a vector, I would not have all the nice properties associated with the mathematics of a vector space. Okay? So on a curved surface, displacement is not a vector. But an infinitesimal displacement is a vector. Now, I'm not being very rigorous here. So if I go from A to a point B, which is very close, that is an arrow that is nearly straight. And therefore, I can think of it as an arrow. I can think of it as a vector. Okay? And this becomes exact in the limit where the 2 points are very close. So I'm talking about infinitesimal displacements. So a position is not a vector. The difference between two sets of coordinates is not a vector, because that is finite. But the limit of infinitesimal displacements is a vector. It is simply the tiny, tiny arrow that goes from one point to another point very close by. It is a straight arrow, even though it is very short. Okay? So that is the concept of vectors. You start with infinitesimal displacements as the fundamental vector. Now, you see, you may think infinitesimal things, how do I handle? But you see, you can easily generate things that are not infinitesimal. If dx is a vector, then this is also a vector. You divide by something else that is infinitesimal. This is essentially the velocity, right? Tau is a proper time, okay? So this is a vector, but it's no longer infinitesimal. Okay? That's how you generate proper vectors. And then we define basis vectors in the following way. Now, let's see what I mean by dp. A vector, I can p, if I move to another point v prime, which is very close by, this vector I call dp. So if I shift the coordinates by a little bit, then this tiny displacement vector I call dp. Then I write it as dx mu times basis vector e mu. And I just rewrite this in another form. The basis vector e mu I can write as this partial derivative. Right? And this idea is just, if you think about this in Cartesian coordinates, the movement of a point P when you change the x coordinate, that ratio is just the unit vector in the x direction, I, right? That's what you call I. And J is the movement in the point when you change the position Y. This is how you could have defined IJK normally, and this is the generalization of basis vectors. Oh, I don't know whether I have this later. Mathematicians sometimes don't even bother to write the P, and they write, say, the basis vector is just this. Okay. And if mathematicians just write this, and they write it as the first line as a definition, you would be totally confused why this would be called a basis vector. Okay? You look at mathematical books, they write this kind of thing. But really, the idea is this. Now, the infinitesimal displacement is a vector. What vector space are they members of? We say they are members of the tangent plane. Okay? So on the manifold, think of it as a surface of a sphere. Every point on the manifold, I put a plane, which is tangent. Okay? So there are different tangent planes. And the infinitesimal displacement is a member of this tangent plane. And this is actually the key idea that links to what we have just discussed. Number one, on each individual tangent plane, you can do everything that you normally do with vector spaces. Okay? You can take dot products, you can add vectors, all right? If it's a three-dimensional plane, you can take cross products. You can ask about length of vectors, and so on. Is that okay? Because it's one vector plane. Everything you learn in vector algebra, you still do. But you see, there is a private vector space for each point. And this is really private because it applies only to that point. Suppose this is a surface of a sphere. This tangent plane is not the same as this tangent plane. So to subtract a vector in this plane and in this plane is highly non-trivial. Right? That is the key problem in Riemann geometry. How do I subtract two vectors in two different planes? So you see the idea exactly the same as when we discussed earlier. You have to parallel transport a vector to here before you do the subtraction. That parallel transport is analogous to the case of in electromagnetism. When you transport a quantum mechanical wave function, you may have to rotate the phase. You do not simply take real part become real part, imaginary part become imaginary part. You actually mix the two as you go from one place to another before you do the subtraction or the derivative. Okay? So you see, it's exactly the same idea. Although one is EM, the quantum phase, here is a vector. Now you may ask, why do I want to subtract vectors in different planes? Oh, okay, so this is just vectors live on different tangent planes, all right? So you have a tangent plane at x, tangent plane at y. They are different. And you cannot naively add a vector in one plane to a vector in another plane. You cannot take the dot product between 10 vectors in different planes. Well, you wouldn't want to do any of those things anyway. But one thing you do want to do is to subtract vectors in two different planes. Why? In terms of physics. You see, in physics, if a particle moves from, say, x to y, and imagine x and y are very close together, just neighboring points. A particle moves from x to y. How would you try to describe the motion? Well, following Newton, Newton's second law tells you what is the change of momentum. Newton's second law tells you that the change of momentum is equal to the force, right? So the first thing you have to ask is, what is the change of momentum? Whenever you talk about dynamics, that is the question you ask. the change of momentum then involves subtracting two vectors in the two planes, because when it is here, it has a certain momentum, which is, of course, a vector here. When it gets to here, the momentum is a vector here. The momentum is just this. Okay? So it's an infinitesimal displacement. That is the fundamental vector, divided by an infinitesimal time interval, multiplied by a constant. So this is just like the ordinary definition of momentum. But now you have momentum living on this plane, momentum living on that plane, and I now want to ask, what is the rate of change of this guy? Okay? When I write this, I am in fact subtracting vectors in two different planes. And that means I have to have a mapping between the two planes. Now, to relate to a picture I showed you earlier today, in fact, this is E, this is V, and remember you have something like this. This is a mapping of the vector space onto itself. Schematically, it is a mapping of this plane into this plane. They are both V, but they are not identical. They are related by a transformation. Okay? So differentiation is a subtraction of two vectors in nearby planes, so therefore it is non-trivial. Non-trivial, that means we need the concept of connection. So let's go back to the ideas we developed earlier. So you have a base space, which is a space of all, say, positions, which is an m-dimensional manifold. In relativity, this is 4. This is space-time. You have a vector space, which is an n-dimensional vector space. Could be anything. If it is a complex wave function, this is 2-dimensional. If it's SUN, this is n-dimensional. This dimension, in general, has nothing to do with this dimension. All right? That is the situation we discussed. But in this case, n is equal to m, because the vectors we are considering are infinitesimal displacement vectors. Okay? This is not the space of n-dimensional SUN, which is where the space is internal degrees of freedom. This is displacements. Okay? So the space of displacements is a very particular vector space, which has the same dimension as the underlying manifold. In this sense, it is a special case of what we have discussed. What we have discussed is an m-dimensional manifold which maps to an n-dimensional vector space. The two dimensions need not be the same, and in fact, conceptually could be different. Right? Think of SUN. So you have a psi, which is psi 1, psi 2, psi 3 of x. This 1, 2, 3, in this example, this space is 3-dimensional. The 1, 2, 3 labels red, green, blue. It's the color index. Okay? The space labels 0, 1, 2, 3, 4 with space-time. Even if I consider a time-independent problem, this x is just x, y, z, 3 dimensions. Even in that case, when m and n are both 3, those two 3s are totally unrelated, right? X, Y, Z is 3-dimensional space. Red, green, blue is 3-dimensional color space. There is no association between the two, even though they are 3 and 3. There is no association, no relationship. Okay? But in Riemann geometry, we are talking about a special case, where, first of all, m is equal to n, and there is an association. The vector space we are talking about is the space of all infinitesimal displacements on the base space. So it's not an arbitrary vector space is called the tangent space. That's what I mean by the tangent space. So Riemann geometry is a special case of what we have talked about. Right? This is the point I want to get across. And actually, by looking at the general case, things actually look simpler than what you may have learned before. Okay. So we have discussed this idea. That the tangent plane is a private vector space for each x, and the connection just connects vector spaces, different vector spaces. Remember, just by borrowing from the general case, because everything we said in the general case can now apply. I don't have to rederive anything, except anything that is additional or special to this case. So we have gamma mu. Remember, it is an n by n matrix. N is the dimensionality of the vector space. And by that, I mean the following. This gamma mu acting on the vector. Now, mu just labels different matrices. Okay? So each matrix acting on the vector, what is the I component? It is the matrix gamma I mu k multiplying the original k component. The ik are just the matrix indices. It is the row and column index of that matrix. And when you multiply a matrix to a column vector, there is an implied summation, which is the summation over k. Okay? That is why, as we discussed before, why gamma in component form carries 3 indices. Right? One index mu describing which direction in base space that you connect. You connect this x to this x along the mu direction. That is the mu index. And in that connection, you have to rotate the vectors. In the rotation of vectors, that's multiplying by a matrix, and the matrix components are ik. But now, the 3 indices are all of the same type, right? Because ik are just displacement directions, because the components in the vector space are just infinitesimal displacement in the base space. And that is why, in this case, ik are not different types of indices. And therefore, in Riemann geometry, we typically write all 3 with the same type of index, and they have the same range. Not only that, you see, in general, these 2 are different indices, and there is no possible relationship between this index and this index. They could even range over different amounts. This could be 0, 1, 2, 3, 4. This could be 1, 2, 3. But now, these 2 indices will turn out actually to be symmetrical. Okay? They will turn out to be symmetrical. That is a property that you cannot even imagine in the general case, right? They are 2 different types of indices. Say a color index and a space-time index. How could they possibly be symmetrical or anti-symmetrical or anything? So gamma mu connects the vector space at x to the neighboring vector space. It's called in general, it's called the connection 1 form. In Riemann geometry, it is also called the Christoffel symbol. Okay. Was because in the context of Riemann geometry, Christoffel was the first one who really studied this. But he did not really understand Christoffel at the time. It's more general conceptual position as a connection 1 form in this sense. So remember, and this is, I revert to the general case, to parallel transport a vector, you have to do this. This shifts the argument, and this causes the mixing of the bases. And the 2 together I called the covariant derivative d mu, which is the ordinary derivative plus a little bit of rotation. And also, in the general case, we proved that gamma can also be related to this. It is how the basis vector j changes with position. And if this, of course, is a vector, I expand it back in terms of the basis vectors. The expansion coefficient is gamma. Okay? This is from the general case that we have already derived. And I am adopting the notation that applies in the general case. Namely, I'm distinguishing between mu and I. Any questions so far? Now, there is one important property in Riemann geometry that has no analog in the general case. And that is, if I give you the metric, you can calculate the Christoffel symbol. Okay. I won't prove this. It is this expression where the comma means a partial derivative. So you take g nu lambda, partial derivative in the row direction. Okay? So 3 terms involving the derivative of the metric tensor, g mu nu, and then multiply by the inverse matrix. That gives you the Christoffel symbol. Now that's something I won't derive. Those of you who are in the relativity course, you know how this comes about. That, again, has no analog to the general case. Okay? Because the general case, the vector space, has nothing to do with the underlying manifold. And there's no way you can derive the connection by simply looking at the property of the manifold. In Riemann geometry, the tangent space is completely determined by the properties of the manifold. And therefore, you have this expression, which is unique to the case of tangent spaces, Riemann geometry, not to the general case. So that is the Christoffel symbol in Riemann geometry. Then the curvature tensor, again, we just take what we have derived before. The first line is something we derived in the general case, where R and gamma are n by n matrices, right? Because that just comes about from the statement that D is just ordinary derivative plus gamma. If you just take this expression and commute 2 of them, the commutator between 2 of them is just R mu nu. You just get this expression, right? It is the anti-symmetric derivative. Notice these 2 terms alone would be like EM. In the case of EM, gamma is just essentially just A. So it's d mu A nu minus d nu A mu. It's sort of like curl A. It's the EM field. But now you have the commutator between 2 gammas. Now, the first expression is a matrix expression. Each gamma and each R is an n by n matrix. It's actually very easy to remember. Now let me try to write this down in terms of the matrix elements. They are n by n matrices. So if I look at the ij element of this matrix, all right? So in this term, the only matrix is gamma, so this is the ij element. This is the ij element. Now, how about the commutator? Let me write the first term. The commutator is gamma mu, gamma nu, the first term. I want the ij element of this matrix. Well, in any matrix, when you have the ij element, what you do in a matrix multiplication is that the indices next to each other are summed, right? This is what happens under matrix multiplication due to the general law. Now, don't be confused with the mu and nu. That's just being carried along. If you have a product matrix ij, that means aik bkj, sum over k. That is the rule of matrix multiplication. Okay? And likewise for the other one. So if you write it out in terms of the components, this is what you get. Now, depending on your convention, how you define a curvature tensor, some books define it with an over or minus sign. Okay? That doesn't really matter. And in general relativity, people don't write ij. Those are also written as Greek indices because they're the same type of index. And this is the second line, is the formula I derived in your general relativity course. Okay? It may, when you first learn it, it may seem very difficult to remember how all the indices go, right? But you now think about it in terms of the first line. And the first line, you go back even one step to this expression. It becomes very simple, right? Much easier to remember. It's not just a matter of remembering. If you can remember it easily, that means you have a much better understanding. And also, you understand the relationship of these ideas to the idea of covariant derivative in non-abelian gauge theories, even in EM. Right? In the case of EM, this expression becomes R mu nu is del mu gamma nu minus del nu gamma mu, which becomes del mu A nu minus del mu A mu. Okay? So this is essentially the EM field tensor. So I hope the mathematical structure, once you understand it, actually ties in two concepts which superficially seem totally unrelated. One is the idea of curvature on a manifold. The other is the idea of the EM field as the curl of the vector potential, and the vector potential as a connection one form that relates the phase convention in different places. Okay? Start with quantum mechanics. You have the phase convention. The phase convention differs in different places. That requires a connection one form. The connection one form is not constant, and that is what happens to F mu nu. Okay? And this mathematical structure turns out to be so similar to the mathematical structure that describes a curved space. Nothing to do with EM, nothing to do with interactions. You don't even have to talk about physics. You just talk about geometry. The geometry of a curved space, you have to introduce these concepts. So putting all these together, people now say that EM and non-abelian gauge theories has a deep geometrical basis to it. All right? It can be described in the same concept. Now, I will next quickly go to the Einstein's equation. I think that's next. But I think you should, in your mind now, have the following question. What I have described is a formal resemblance between two things. Okay? Curvature and EM. Let's even forget about non-abelian gauge theory for a moment. That's a little bit more difficult. Just take two things which are very simple. EM and curved space-time. Curved space-time is gravity, okay? And you have a deep formal analogy in terms of the mathematics. Question, is there a deep physical unification behind this formal analogy? The reason that they are described by similar mathematical constructs may suggest to you that there is a formal deep relationship between the two. And therefore, one possible path to the unification of EM and gravity. All right? And of course, also with non-abelian gauge fields. And this is one of the routes that people pursue when they look at unified gauge theories. Look at EM as a gravity and EM somehow together using these mathematical language. Think about it. This is one step beyond, in fact, many steps beyond, and in fact contradictory to something that even high school students think about. Why? High school students say Coulomb's law is 1 over r squared, right? Newton's gravity is 1 over r squared. Well, the mathematics are the same. Doesn't that provide a basis for a common understanding or unification of the two? electricity and gravity? The answer is certainly no, okay? Because we have learned much more. Because EM is not just Coulomb's law, it's Maxwell's equations. And Maxwell's equation, when you look at it deeper, has to do with the quantum mechanical phase, and therefore has to do with these connections. Newton is also, gravity is not just Newtonian 1 over r squared. That is only an approximation, okay? The correct theory is Einstein general relativity. And if you want to seek some commonality, some unification between the two, you now know enough not to seek it at the level of saying 1 over r squared, 1 over r squared, they must be the same. Okay? You must seek it at this more sophisticated level where they both speak of connections and curvatures. Is that okay? Except, you see, I won't, today I have only, because there will be course evaluation at 11:05. Let me see what's next. Yeah, I won't go on to the next topic. That I will complete on Wednesday, right? Because I want you to don't get too mesmerized with the details. Take one step back and ask the following question. Can you pursue an analogy? Turns out the most naive thing you want to do runs into trouble. Look at this expression. This tells you that the EM field is like the curvature in general relativity, right? Now, I ask the following question. What does Maxwell equations look like? That is the equations that control EM. It looks as the derivative of the curvature is equal to the source, right? Source is the 4-vector current. I don't even write indices. It's a first set of first-order equations satisfied by F, or the curvature. Okay? What does Einstein's equations look like for general relativity? Well, this source is the current J. It is that the curvature tensor is equal to the energy momentum tensor, right? Not quite the curvature tensor. You have to form the Einstein tensor and so on. But basically, you don't have to take another derivative. You just have to combine components, right? If they are similar, you would have guessed it should be an equation on the derivative of the curvature tensor. If this is correct, then this can only satisfy an equation like this. So that you are naively led to think that if you pursue this analogy and this analogy actually works out, maybe Einstein's equations, you should look at it with one more derivative. Derivative of curvature tensor is equal to the source. The source in this case must be the derivative of the energy momentum tensor. Anything that satisfies this equation must satisfy this equation. That's okay. And this would have a formal analogy. Maybe you can combine everything together into one theory and seek unification. What is the problem? Well, turns out it's not so easy, because if I look at this theory, look at the limit of weak fields, slowly moving particles, that gives you the Newtonian theory, which is, roughly speaking, Laplacian of the gravitational potential is somehow related to the mass density. Okay. So if you believe this, it must somehow end up with one more derivative. Okay? It's okay one way. The solutions that we know about, that is, the solutions that satisfies the bottom equation, must also satisfy the middle equation. Because left-hand side equal to right-hand side, you take one more derivative on each side. That's okay. But the reverse may not be true, because there are solutions that satisfy this one, but not this one, right? Namely, schematically, you can. If it's well, it's not quite a simple derivative, but even if it's a simple derivative, that means r minus t is not 0, but a constant, right? Those are extra solutions. So either this does not work, this guess runs into trouble, this is not a fruitful possibility to pursue, or maybe there are extra solutions that Einstein didn't think about, but this analogy gives you. Do those solutions make sense? If they are new solutions, there must be new phenomena in the gravitational world that we have not thought about. Okay? Do you understand the question I'm trying to pose by just pursuing this analogy? Now you have to work out the details of how the indices go and the details and so on. Actually, the answer to this question is no. I won't tell you the answer. Whether you run into a wall and it cannot be done, at least conventional wisdom tells you that it cannot be done, namely that the extraneous solutions do not make sense. Right? Between the second line and the third line, the extra thing are extraneous solutions. Okay? Whether the extraneous solutions do not make sense, and therefore this line of thinking is nonsense, or whether this line of thinking is actually reasonable and there are extraneous solutions that point to new physics that you should do experiments to look for. And the point I'm trying to make is the following. In theoretical physics, in the frontiers, not everything will be right. You have to try out various possibilities that the mathematical structure suggests to you. It may or may not work out. The main idea is not how to work them out. That's just algebra, okay? It's just algebra. Anybody with enough, algebraic ability can do it. It's being able to look at the patterns and ask significant questions. And if you step back enough from the detailed algebra and look at the structure of these two theories, this is certainly a question that you are led to ask. Okay? It would be dumb if you do not pursue this question. Whether or not pursuing this to something useful or is a blind alley, you don't know. When you pursue ideas in theoretical physics, 9 times out of 10 they will be blind alleys, 死胡同. All right? But maybe 1 time in 10 it will lead to something. But any theoretical physicist who gets to this point certainly will ask this question. All right? And this question, let me repeat, comes from the following. EM is the derivative of the curvature tensor equal to something. Field is the curvature tensor. A is the connection. Gravity is the curvature without derivative equal to something. At that level, they don't come together. If you want to force them together, one way is to take one extra derivative on the gravitational theory. Okay? Again, I said I won't tell you what the answer to this question is. I want to leave something open for you. If you look, it's actually in the literature, this thing. But maybe the answer in the literature is wrong. I don't know. We can't say what is right, what is wrong, because it's wrong or right according to a set of implicit assumptions, right? If you break some of the implicit assumptions, right could become wrong, wrong could become right. Okay? For example, some of the paradoxes in special relativity, you can prove is right or wrong under the implicit assumption that there is a universal time. Your time is the same as my time. Then you run to certain conclusions, right? And when you started out, 100 years ago, this is so obvious that you don't even state it as an assumption. It is implicit, and so you rule certain things out. But maybe you can get to some new physics by realizing that there are certain implicit assumptions, and at a certain point asking whether or not those assumptions need to be dropped. Okay? And very often, the assumptions are so natural, so implicit, that we don't realize they are assumptions. Okay? And the creativity comes about when you do realize that they are assumptions that could be relaxed. One example we have dealt with the monopoles is the assumption, you see, must have been implicit before you take this course, that the vector potential must be a single function defined over all space. Right? When I ask you what is the vector potential, it is one single function. You never thought about it could be one function here with an overlap, and it's together that's what I mean by a vector potential. Right? That is certainly a relaxation that you never thought about. And once you realize that you can do that relaxation, the rest of the algebra is actually, not very fancy. Okay, so don't take everything for granted. There may be other relaxations that could lead to various things. That's the whole idea of the more formal part of mathematical physics, theoretical physics. How come it's not yet here? Okay, so let me just stop here today. Don't run away at this course evaluation. And on Wednesday, I will finish with this. But let me now pause for whether there are any questions.
In these classes, you are talking about the localization all the time, and you can even put in localization in quantum mechanics with the local phase factor. But my question is, in standard textbook, the wave functions is defined in the global inner product space, the so-called Hilbert space. And if you put in localization in the wave functions, and I'm wondering whether the orthonormal conditions still hold.
Very good question. Now, in quantum mechanics, we have an idea like the abstract idea of an inner product, where psi and phi are abstract objects, right? Normally, you define this as the integral right? Now we have done the following. This is base space, and I may have, let me cover base space by two patches. So there is one patch which I call little a, one patch which I call little b. Actually, psi is really two things. It is psi a and psi b. This defined on a certain patch, that defined on another patch with an overlap, right? It's not a unique wave function. There are two functions in two places, right? So how do I define this integral? Well, it is okay if psi star phi, whether you use A and whether you use B, well, that's it. That is, when you do this integral, it's okay. Here I use A, here I use B. Your question is, what do I do here? There are two definitions. I can either use the A version or the B version. But think about it. They are the same in this product.
So there are extra conditions.
Oh, yes.
Extra constraints for this kind of method.
Yes. That is, in this case, it is U1. Okay? In other words, all the physical quantities you want to calculate must be invariant with respect to your transformation group. Here, my transformation group is multiplication by the phase e to the I theta, which can be position dependent, right? But you see, this transformation doesn't bother this. All your physical quantities must be invariant with respect to the transformations. So let's continue with the general relativity in a second. All right?